Okay, let's begin today. So that was a brief course matters, and hopefully by this time you access the assignment 1, hopefully, and there was some questions. Anybody started your assignment yet? No, not yet. Please take a look at it. It's going to be okay. Okay. Anything else? No. I will definitely let you know about that. What's going to happen on the first week of April? I will let you know sometime in 2 weeks. I will let you know. Okay. So we were discussing what on Monday? We're discussing a pseudocode, but in slightly different looking ways, right? What was the reason that we started discussing this stupid looking notation? What was the reason that we started discussing this type of ideas? What was it? Simply, we wanted to have some kind of mechanism to compare two different algorithms, maybe. So, which algorithm is better than the others? And then we start bringing up in this notation most of the part we've been discussing for something called time matters, time complexities, right? How fast, but it should be careful. Sometimes it's not about the time. It's maybe we used a term like comparisons. How many comparisons can one algorithm can do it, the other algorithm cannot do it, right? See, that was the stuff that we start discussing, right? What was the first sorting algorithm that we start discussing? What's the name of the algorithm? Who saw? What is the easy search? Selection sort, we start discussing on the selection sort part, right? And then we said something like big O of n algorithm and linear algorithms, right? And then I was drawing a graph, like linear means just straight line going up. Yeah? Oh no, selection sort is not a linear algorithm. Selection sort is n square algorithm, n times n, right? Sorry. Sequential search was a linear algorithm, right? I usually remember it this way. If I given an algorithm and I don't know too much about this algorithm and I also don't want to read it, but I see the idea and then it goes to me like, okay, in order to do something in this algorithm, I may need to do all the comparison between the elements, or just comparison needs to be done just for the n times, or total number of elements in the list. Then it's going to be a linear. It seems on other type of algorithms, it seems if I write a pseudocode, then if I feel like I should need a loop inside a loop, right? If so, then there might be high chance that my algorithm will have a n square running time algorithm. I also take a look at it that way. I try to think of the easy ways of doing it. Selection sort, why it was an n square algorithm? What was the general idea? Oh yeah, we did. Monday면 it's just a day ago, 2 days ago. See? It has to have according to the algorithm that is given in your textbook, it was given a subtask, right? So smaller algorithm inside the big algorithm. What was the smaller algorithm that they are referring to? 피곤하네, 갑자기. Well, finding largest or finding smallest depends on which way you want to sort it, right? So every time you look for an element that is largest, for example, largest is in the list, and then you get the largest value and take it out, give it to a new space, a new list, and then you do it again for whatever left on your list, right? That's why we had the big loop and inside the small loop. So 뭐야? 왜 이래? 왜 이래? What's going on today? Huh? Did you guys have the lunch? Coffee? No? Next week, coffee, please. 먹고 들어와. 그죠? Next week, 먹고 들어와요. Sequential search that we know, the T, N, if I'm looking for certain names, if name is existing in the list, then I can print out the T telephones, right? Linear algorithms that we discussed. I don't need to draw that graph again. So, and I also start giving you some ideas like if n goes to infinity, then which is better. Also, we were discussing this one too. What if you have a choice of two different algorithms of running time? Comparisons. I say comparisons, right? It means we're still discussing a time complexity matters. So, n beats n square. Can you give me a point that where the n square algorithm exceed the linear algorithm? Right? Things like this were discussed. 아니야, 맞아, no response, yes, no, 그냥 끄덕이기라도 해요. Please not. 그죠? 아, 피곤해. 갑자기. Right? Well, of course, with the differency constant, you will have a different values for crossing point and stuff. Hopefully, you will be able to understand what it means to have such point in there. Also, another careful things to remind yourself is, it doesn't mean that always n square algorithm is slower. In this case, I guess, up to this point, the linear algorithm is much faster. So if you have a certain boundary, then sometimes it's okay to use an n square algorithm or n cube if you wish. Right? 그죠? Comparing the algorithm efficiency. Efficiency is the key term that we try to use, efficiency. 그죠? Part of the job of the programming documentation. Write it down. This is my pseudocode, and this pseudocode is n square algorithms. Okay. Might be helpful for some others. Programming documentation it's in the software engineering area, so we're not going to discuss that too much, but just being nice. Think of it as a being nice. Does your programming courses ask you to put a comment or any type? When you do a print hello / this line is doing print hello, you try to explain what each line does, right? So in some cases, probably not for the all lines, but that's one of the steps to start a documentation. That's very helpful habit to have later on. Am I speaking too fast? Yeah? Okay. And I explained it. Algorithm A depends on the C value. The growth ratio was slightly different. 그죠? And then I think we stop around here. 그죠? Now we have a first set of examples for comparing the efficiency. We'll see time matters. We know what notation's meaning for. It's actually theta, but I keep referring to it as a big O. Don't worry about it. It's in the order of magnitude, and it's good enough at this point. Okay, so they give you now three different set of algorithms. Three different algorithms, but it's going to do the same thing. It's going to do the same thing. Which one do you prefer? We don't know the time complexity yet. We don't know the space complexity yet. We don't even know what they're doing at this point. So just your gut feeling, what would you use? Or what might be the easiest one to implement? If you're given a choice and three algorithms, which one do you choose? Are you going to choose the algorithm that is faster and nicer, but it's a bit difficult to implement? Or you're going to choose the algorithm simpler to implement, but time efficiency is not so good? Which one would you prefer? 쉬운 거 하겠지 아마. Simple implementation. Right? That's also okay too. If that's your design decision, I don't mind. 구현하기 implementation means 구현. You actually write a program. That part. Come up with the algorithm. 쉬운 거 선호하기도 하겠죠. 나도 쉬운 거 선호해요. That's because our computers nowadays are so nice. We don't do any of the lower level embedded programming yet. So just your computer can do anything. So I don't usually care about time and space complexity at all. So there is no right or wrong on choosing which one to use. So let's take a look at what data cleanup algorithms does. Shuffle left, copy over, and converging pointer. Nice names. Actually, names speaks itself. Self-explanatory. It's pretty much the entire algorithm is in the title. Shuffle left. Okay. 어디 갔니? 이제 슬슬 알고리즘만 계속하니까 지겹죠? Just stay in this chapter. Next chapter, they probably start discussing something else. 첫 시간에는 너무 생소한 거예요 막 이러더니 이제 두세 번 하니까 이제 지겹다는 얘기가 나오기 시작합니다. 어째야 되나? Okay. Given a list. Okay. I'm just going to bring up any example. Okay, this is position 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's make it 10. Okay. And it's not empty. Everything has numbers in it. So it equals 10. Okay. Just give me any number. 4, 0, 2, 1, 9, 0, 0, 4, 3, 2. Okay. All this try to ask is remove zeros from this list. Remove from this list. Okay, I say 1, 2, 3, and then this will be input, output. Could be many different, but one of them might be like this. 4, 2, 1, 9, 4, 3, 2, 0, 0, 0. How'd you do this? That's why they say cleaning data algorithm. They look at zero as and garbage. It's garbage. I like to remove the garbage from the list. Shuffle left algorithm give you quite simple pseudocode. Scan the list from left to right. Okay. Left, right. Start from here. Okay. When 0 is found, or no, not 0. Next position 2, 0. 0 is found. Copy each remaining data item in the list one cell to the left. What does that mean? If I write this down. 아이고 잘못 쪘다. 손을 지울 걸. I would like to copy on this side to the one move to the left. 2, 1, 9, 0, 0, 4, 3, 2. I don't know, it's leftover. I could say 0 or just leave it as it is. I'm moving everything by 1. Shifting. Shuffle left. Shuffle이 뭐야? What is shuffle? 셔플 댄스 이런 거 말고 셔플이 뭐야? When you go to casino, 카지노도 안 가봤지. 카지노 갈 리가 없지. 카드 섞는 거 일반적으로 셔플이라고 많이 하죠. 카드 섞는 걸 셔플 한다고 그러잖아. 카지노 가본 사람 혹시 마카오 어디 가봤어요? 오, 뭐 하는 사람이에요? 둘 중에 대부분 하나만 가볼 텐데 둘 다 가본 사람은 또 처음 만나보네. 거기 가면 카드 막 이렇게 섞죠. 셔플링 한다고 얘기하죠. Anyway, in this case, we're shifting numbers to the left. Shifting numbers to the left. Okay, we're gonna do this. Probably after this point, we're gonna move to here. Next point, do the same thing. One big loop process. I'm gonna have to go through every single element in the list. 그죠? And then every time I see something like 0, what should I do? Copy whatever remaining to the 1 left. This might require another loop too, right? I have to move 1 by 1. That might require another loop. So in big loop, inside the smaller loop, but smaller loop will move leftovers to 1 to the left. How can I move something to the left? This array structures, list structures. There's a reason that I have this position. So I changed the position of each number. Originally 9 was in position 5. I'm gonna say when I need to ship this, 9 will be at position 4. That's the process of switching it. Okay. And that's a basic idea, general idea of doing it. And even without looking at the actual pseudocode at this point, what might be the possible comparisons? What type of algorithm of this in terms of order of magnitude, in terms of n? You go, what's a running time complexity? N square. 그죠? I don't need to look at the pseudocode yet because one big loop, each smaller loop, I move. So it's most likely it will be n square algorithm. Already found the answers. So sometimes you don't need the complete algorithm to guess how it does. Can I find a smaller algorithm? Yes, maybe. There might be a better algorithm in terms of time complexity, but a simple idea seems to be require n square algorithm. 그죠? Okay, you already have an idea. What's the next step that I usually ask? Write a pseudocode. Write a pseudocode to express this. In order to write a pseudocode, they suggest that you need certain variables like length, I think legit. I'm going to call it as a legit, but it's a length of the list. Length of the list. So somewhere in here, originally 10. 그죠? Originally 10. Maybe I'm going to start from 1. As I move, I'm going to increase by 1. I know total number is n. That might be one of my looping conditions. When legit hits 10, I should stop or something. I had to declare certain stopping conditions for the loop, right? Exit conditions for the loop. It's reduced by 1 every time 0 is encountered. Okay. In this case, they suggest I'm going to set it as a 10 every time I see a 0 minus 1. So later I have 3 zeros, so it's going to be 7 at the end, right? So that's, I removed 3 garbage data from the list. Okay. That's the algorithm for this. Let me do it again. It's going to be boring, but get value of n and n for the data. Okay, n is ready, and 10, list 10 ready. Set the value of legit to n, which is n is 10. So set the left. I need another variable called left to what? 1. Right? 1. While left is less than or equal to legit. Okay. While 뭐지? Legit less than equal to what was it? Left to. Do what? If the item at position left is not equal to 0. 내가 뭐 잘못했나? 미안. 2. And I do that too. If the item at position, 눈이 멀었나 보다. 이렇게 보면서도 엉뚱한 거네. If the item at position left is not 0, how do I express that position? I'm going to put this array as a L. Okay, L. Okay, if L's position, left position, is not 0. L left means left is 1, right? As first is 4. As 2 is 0. Okay, I'm going to write that way. Then what? Increase left by 1. 이렇게 하자. Left plus 1. 그치? And increase right. What is this doing in this case? 뭐 이제 뻔하지 뭐. Left here. My left is pointing. Right is pointing. 그죠? This is my initial 1, 2, 1, 2. Let's say I'm going to change to 3. 아니다, 0 is okay too. 0, 3. Left, right. I'm comparing 4 to, it's not 0. I need to go to the next one, right? Plus 1. So this is going to be my left. This is going to be my right. I'm keep moving this way. That's why I'm keep adding it up. So, adding it up. That's the one. If it's equal to 0, so S. If left is 0, do what? 여기다 뭐 하게? Why? If item of position left is 0, do step 10 to 14. Reduce legit by 1. 그치? 내가 이거 왜 다 쓰고 있지? 다 알면 그만하라고 얘기 좀 해줘요. 이거 굳이 안 해도 되는데. And then while I'm in the while loop inside the else. While again checking. Right is less than equal to n. Right is less than equal to n. Copy the items at position right to a position right minus 1. Right position here. But in this case, if it's a 0, then 2 to 1. So how can I copy? 뭐 다른 게 필요한데, maybe I can do this. Right should be L right plus 1. 이거 정확하지 않아요. 이렇게 하면 안 돼. 이렇게 하면 나중에 fail 하는데 지금 현재 있는 자리에 그 옆에 있는 걸 갖다 넣는 거예요. 그냥 right plus 1이라고 했어요. 맨 끝에 가면 어떻게 돼? right plus 1이 없으면 에러 나겠죠? 그죠? 이렇게 하면 안 돼. And then increase right by 1. I need to go to the next one. This way. Copy here. Maybe I can ask you a question later for this part. This is temporary, or maybe I can remove this part. Ask you to fill out this part of the code. How can you copy of the next one to the current position? 이거 typical questions look like. I'm gonna 이렇게 다 해놓고 I'm gonna empty. Fill out this part. Your midterms or finals will look like this. 중간고사나 기말고사에 물어보는 문제가 이렇게 될 거 이렇게 써놓고 여기 중간에 이렇게 지워놔요. 여기 써 이렇게 하는 경우. This one, copy part. Write it. And then increase by right. You can just simply follow whatever they're doing. Plus plus. Set value left. Left also need to go to the next, so I can continue. So done. That's a rough. That's not rough. That's a complete algorithm for doing this. This simply translating to that, but we just need to be careful with this new variables like left, right, regit, and looping conditions. So that's a shuffle left algorithm for data cleanup. Okay, I think we understand the time complexity part. And then if this is a algorithm or program, if you want to call it, then what's the total memory space that I need? Memory space. L must be there. 그죠? L is already given. And I need maybe a space for legit, left, right, maybe even for n. I need 4 extra spaces to store a number. Store a number in order to implement this. 그죠? To analyze time efficiency, identify fundamental unit of work the algorithm performs. Fundamental unit of work in this case is how many comparisons do you do, or how many moves that I do. In this case, also copying numbers. You switching a place moves that you make. Best case. What's the best case for this scenario, this algorithm? In terms of time analysis, time complexity, time efficiency, I should say. What's the best algorithm? Best case algorithms. Best case가 뭐가 될까? Yeah, there's no 0. 10, 9. If there's no 0, I don't do any of the copying operations. Simply just going this way once. And this way once means I'm still looking for 0 in the value. That's my best case input scenario. So in the best case, no copying required. Worst case, everything is 0. Copy. It's quite dumb, right? If everything is 0, I'm copying 0 to the another left. All the 0, 0, 0, 0. I'm dealing with the old garbage. Right? So worst case, probably n square. Best case, if you're good, then n. So you just need to go through the list once. So worst. 밖에서 누가 소리를 지르네. Best case, worst case, 2 different scenarios. Worst case, it has all 0 values in n square. I must do n square algorithm. Space efficiency, like I told you, given a list that's already given n space, I need 4 extra spaces to do this. So n memory location for n, left, right, that's it. This is a location to store a number. 그치? Well, if you wish, you can remember in this way too. N plus 4. We just done analyze shuffle left algorithm in both space and time efficiency way. Good. 그치? 이건 quite simple, right? Quite simple. But what if I start asking you to come up with the algorithm that, in worst case, do it in n? Even in worst case, I like to remove this stuff. Even everything is 0, I like to come up with the algorithm that does this in linear time. Can you come up with the algorithm? 이거는 worst case 다 0일 때는 n 스퀘어밖에 안 되잖아. worst case 다 0일 때도 n으로 할 수 있는 알고리즘을 찾아와라 그러면 어떻게 해? 뭐 어떻게 해? 못한다 그러면 되지. 모르겠는데요. 꽤 괜찮습니다. 모르겠다. Is there going to be a minimum boundary? I mean, 뭐 어떤 알고리즘은 어떤 문제는 절대 n 아래쪽으로는 풀 수 없다. Can you prove that? 증명할 수 있어요? 어떤 알고리즘 나중에 증명하는 게 나와요. 이 과목 말고 다음 학기 하는 거고요. 어떤 특정 알고리즘은 n 아래로는 절대 내려갈 수 없다라는 거를 증명하라고 이렇게 나와요. 증명이 되면 n 아래에 있는 알고리즘을 찾아다닐 필요가 없죠. 괜히 쓸데없이 시간 낭비하고. 혹시 n 아래에 있는 걸 발견하면 알려줘요. 혹시 알아? 노벨상이라도 줄지. 그죠? Space efficiency. So that later we'll discuss that more, probably next semester or so. Okay, we're going to do the exact same thing, analyzing time efficiency and space efficiency of the same data cleanup algorithm, but different name. Copy over algorithm. Copy over algorithm. If you flip a few pages, if you take a look at the pseudocode, it's probably longer than shuffle left. Okay. Probably longer than shuffle left. If you see that longer, then it might take more trouble to implement, I guess. 어떻게 하면 될까? Without even looking at that. What's my options? What can I do? Any good ideas? Can you beat the ideas in the textbook? Later, 나중에 보면 anybody interested in this? Have you seen something like programming contest? Programming contest? ACM programming contest. But if you actually take a look at the questions they ask, it's not a programming. They give you a problem and they want to come up with this type of algorithm to solve it. But those type of contests is they only give you maybe an hour to solve. So a group of people studies and go there. They give you a set of problems, and if you can solve more than 5-6 questions within a couple hours, then you're good. In Korean briefly. 나중에 보면 ACM 프로그램 컨테스트 뭐 이런 거 있어요. 근데 가 뭐 프로그램 짜는 게 아니라 똑같아요. 이상하게 뭐 되게 어려운 문제 같은 걸 주고 알고리즘을 제한 시간 안에 주어서 내면 돼. 그거 매년 해요. 매년 국제적으로 매년 하고 하는데 아마 우리 학교에서도 누가 준비를 한다고 매년 나가는 걸로 알고 있는데 아마 꼴찌일 거예요. 그게 좀 희한해서 1등부터 몇 등까지는 등수를 매기고 몇 등 이하부터는 다 똑같아요. 다 29등이야. 그 아래는 뭐 그렇게 안 하고 몰라 요즘 바뀌었는지 모르겠는데 그 문제 이렇게 보면 똑같아요. 책에 나오는 거. 좀 빨리 하는 사람 거는 점수 좀 더 주고 막 이런 식이에요. 근데 종이로 쓰는 거예요. 다 이런 식으로. 혹시 관심 있는 사람도 아마 동아리 뭐가 하나 할 거예요. 동아리 중에 하나가 할 거예요. 그 맨날 1등 하는 학교가 최근에는 몇 년 전까지만 해도 1등 하는 학교가 어디였는 줄 알아요? 몇 년 전이지? 10년 전부터 쭉 치면 옛날에는 이제 미국에 있는 학교들도 하긴 미국에 있는 학교들도 그렇게 잘하지 못했는데 한동안은 러시아에 있는 막 이상한 막 피터 상테스부르크 대학 이런 데가 막 컴퓨터로 유명한데 막 이런 데가 막 1등하고 그러다가 최근에는 어디가 1등하는 줄 알아요? 뭐 맨날 1등하지 못해요 하는 데가 요즘엔 중국에 있는 학교들이 1등해요. 상하이 교통대학 뭐 이런 애들이 얘네들은 뭐야? 리스트 보는데 얘네들은 뭐야? 뭐 이러면 갑자기 튀어나오는 애들 똑똑한 좋은 학교예요. 그런 학교들도 참고로 말하면 뭐 MIT 이런 데가 10등 안에 못 들 때도 있어요. 그래도 걔네 꾸준하게 그래도 한 4, 5등 안에 들긴 하는데 뭐 CMU 뭐 이런 학교들도 들긴 하고 가끔씩 그 캐나다에 내가 나온 학교가 1, 2등을 할 때가 있었어요. 근데 나 걔네들 얼굴 본 적이 없어. 동기들인데 걔네들은 1학년 때부터 같은 수업을 들어도 걔네들은 클래스가 틀려. 그러니까 같이 수업을 들어도 쟤네들은 우리랑 얘네 신, 우리는 일반인 막 이랬던 애들이 있어. 관심 있는 사람 한 번씩 봐요. Same idea. Copy over algorithms. Scan the list from left to right, copying every legitimate non-zero values into a list it creates. Same idea. This time, they wanted to put a non-zero values, which means into a separate list, which is quite similar to the examples that I give you for the selection sort. Right? My selection sort algorithm that I show you on Monday. So, it was also when I see a largest value, I create a new list, put that in. Right? So instead of moving around within the list, they create a new list just containing non-zero values. That's the basic idea. Every list entry is examined to see whether it is a zero. Every non-zero list entry is copied once. So best case. Or before you even look at this, yeah, it may be okay. Best case, if all elements is zero, then what? No copy. So, order n. No extra space is used. Okay. 아이고, 미안. Shoot. What about worst case? What is the time efficiency of the worst case? In terms of comparison, I think it still be n, right? But we need to sacrifice another thing to receive this n time efficiency. 0, no. 1, okay. I create a new list, my list, 1. Next one, 1, 2, 0, no. 아이고, 0 하면 안 되지. Done. In terms of comparison, same thing. I just keep doing once. If there is, I just copy once. It's not a looping procedure. So even in worst case, it's going to be quite similar to a n. Best case now, worst case now. Best case now, worst case now. It's going to be close to linear. Okay, let's take a look. I guess I can just read it now. 그냥 읽어도 되겠다. Get value of n list, we know. You're going to set the value of a left to 1. 1, 2, 3, 4, 5, 6. Left is 1, left. Set the value of new position 1. New position 1, 1. This is new array 2, 3, 4, 5, maybe 6. New position 1, new position. While left is less than or equal to n, while 1 is less than n. If the item and position left is not 0, then do step through this. Copy an item position to new position. If it is, copy, not copy, copy, not copy, copy. And then you just move this pointer increase by 1. So if you look at it, big while loop, no while loop inside, just if statement. So even in worst case, it's going to be just n. In terms of time efficiency. Makes sense, 그죠? Makes sense. But what do I have to give it up? Or what do I have to give it more? In terms of space efficiency, I have to provide this extra space. 그죠? I have to provide extra space. If the previous shuffle left algorithm requires only n plus 4 spots, this one maybe 2. This is space that I need, right? Because I need exact same size. 사이즈는 똑같아야 되겠지? What if everything is a non-zero? Then I need to. So this copy over algorithm requires more space, but in terms of time efficiency, it's faster. Okay. I can do it. My computer is big enough. My memory is big enough. I can always give, even if they want, I can give thousands. Okay. Thousands. Doesn't really matter. I can do this. So they call it as a trade-off. What is a trade-off? 트레이드오프가 한국말로 뭐지? Trade-off. 하나를 gain하면 하나를 포기하는 거. If you gain something, you need to give it up something. So it's always important to have a balance. So it's a space and time efficiency trade-off. 여기는 속력을 모든 케이스에 좋게 하기 위해 메모리를 좀 더 주고, 아까전 같은 경우에는 메모리는 훨씬 적은 대신에 속력이 나쁠 수도 있는 거죠. worst case에서. So that's the trade-off. That's the trade-off. If I write it, both algorithms, shuffle left was worst case, best case. 이거 뭐지? Copy over algorithm, worst case. 됐다. Okay. But what about space, memory? Shuffle left. I'm gonna just say n. This one. If I come up with a new algorithm, what do I want? What do I want? If I give you third algorithm, first algorithm, second algorithm, what do you want me to write here? 보긴 뭐겠어. It would be nice to have something like this. If you compare it to the previous two, if some algorithm can do this, better. Is there one? What if I ask you to build one in your assignment? 어떻게 하겠어? 분명히 시험 같은 데 나와요. I will ask you to build one of your algorithms or even another assignment. 그래서 나중에 보면 그림 그려놓은 사람들이 많다고 내가 얘기하는 거야. 죄송합니다, 그림 그려놓고. 캐릭터 그림 그려놓고 막 이런 사람들 많아요. 시험지는 문제는 하나고 이만큼 비어있거든. 그림 그려놓은 사람 많아요. 그림 그리면 안 돼요, 시험지에. Worst case, time efficiency. I hope you get the idea for trade-off by looking at that table. The third algorithm that we left, is it going to achieve that performance? Converging pointer algorithm, will it be able to make this condition? 그러니까 나왔겠지, 그죠? So, it's there. Converging pointer. I know you guys haven't taken any courses on the using pointers and stuff. Let me give you a very, very simple idea for a pointer. What is a pointer? Vocabulary, pointer. Location 1, 2, 3, 4, 5, 6, 7. Pointer simply means I'm pointing here. Pointer, that's my pointer. I'm pointing here. That's my second pointer. Converging. What is a convergence? Convergence가 뭐지? 뭐 융합 이렇게 많이 표현하잖아요, 융합. That's a very fancy way of translating. Converging. I move this way, I move this way, I meet somewhere in the middle. If you have that idea, can you build an algorithm using this way? So they use a term like swap. Swap zero values from left with values from right until pointer converges in the middle. Pointer converges in the middle. Until this happens, I'm gonna swap. Swap means switching. If it's a 0 and 1, I'm gonna swap 1 and 4. Then 1, 0. Swap. Swap operation. That's the key idea for this. What's the best case in here? Actually, best case is always the same. All right? No 0 elements. Everything is a certain number. Then you don't need to swap anything. So, worst case, everything is 0. Log n in time efficiency and is space efficiency. It seems I don't need extra list. Okay. It also says, I don't know how, but also says if I do this, everything will be done in n times. Linear times. Okay. Third one, right? We have a winner. 이름 까먹었다. Converging pointer. Converging pointer. I guess in your textbook, yeah, like that. They give in a box and let you practice on those boxes where those pointers are located every time you execute each line of the pseudocode. See? How can you practice? Just do it once. No, not once. Do it a couple of times. If it's okay to use the numbers in your textbook as a list, or if you're done with those numbers, you can create your own list and try it once. What's the values going to be? Left, right, how do they change? How does the legit value will change on different algorithms? So try to write it down. Each step, I would like legit, something left, something right, something, and then this is my first loop, second loop, same thing, but value is what, value is what, value is what, and pointer is pointing to where. I would just write it down. Do it once, you would know what it means. But you need practice to follow the pseudocode. Okay? Even if I give you an algorithm that you've never seen it before in your exam, you don't know the time efficiency. But maybe you can just do it this. Do it like just one step. Just give 3 numbers and try to do it, and you can guess what's going to be a time efficiency and space efficiency. 그죠? 답을 모르면 손으로 한번 적어보면 금방 감을 잡을 수 있겠죠? 그죠? Same step is being asked in your textbook and the assignment. Okay, so same step. First few lines always same. Get the values for n, the n data items. Okay, I'm still going to need a legit somewhere in here, but I'm gonna set legit as to n, left to 1, right to n. Before left and right always start from 1 or 2, 1 left. Right is coming from the end of the list. While left is less than right, always left will be less than right. If the item position is left, not 0, increase left by 1, means if it's not 0, I go to the next one. So, else, if left pointing is 0, then I'm going to do this. Reduce legit by 1, because there is a 0 found in the list. Total elements in the list should be decreased by 1. That's the same step. And then copy the item and position right to left. 어디 갔니? If my first value is 0, this my left is 1, left is 1, 2, 3, 4, 5, 6, 7. Right is 7. Swap. Whatever value in here, 0 here. Swap. And reduce right by 1. 6. And then you go back up again. Notice that if this happens, left didn't change. Left didn't change. What if the value was here is still 0? So I need to check here again. Let's check here again. Left didn't change. If value that I swap is not 0, then I can move to the next left. At the same time, right already shipped by 1. Here. Now it's pointing different value, 2. And at some point, either this goes this way, either this goes this way, meet. Then done. Meets means while left is less than right. So if they equal, I break the loop. 그지? left랑 right가 같으면 더 이상 이 안에 안 들어가잖아. End the program. Non-zero element will be on this side. Zero element will be on this side. 그치? Does it make sense? 쉽지? 쉽지. 잘못 짜면 어떻게 되겠어요? 잘못 짜면 if you careless, your condition is not right, then you might if the value was here even 0, it was 0, swap 0, but you didn't check this one, go to next one, then it's a problem, right? Be careful when you do those type of things. Sometimes you misunderstand. Swap doesn't guarantee the value that you are swapping is 0 or non-zero. Okay? If you try to do this without the answer sheet, a lot of cases will be like that. You kind of just skipped it. You forgot to check the again. Going to the next step. 이거는 the pseudocode that present in your textbook is nicer ones. Very nice looking ones. I don't expect you to write this from at this point. It's going to be difficult. Right? Your algorithm will be much less messy. 아마 쓰라고 그러면 막 라인도 더 많고, some people require 30 lines of doing something. On the other hand, this one just requires 12 lines. That's completely okay. That's completely fine. That's normal process. If you have more experience, hopefully you can reduce lines like this. Later you come up with this. Okay? In order to do that, you need to practice, think. Solve the questions in your textbook that I asked for. Hopefully, end of this term, then you will be able to write it something like this. Table. Okay? Shuffle left, best, worst, average, all different, but space, space, space. Nice. Everything is N. Doesn't matter whether best case, average case, worst case. Forget about the average case at this moment, okay? Forget about the average case. I only care about the worst and best case at this stage. Nice. So what would you choose if you're given a chance to implement this in C? Which algorithm would you use again? Doesn't matter. Just use whatever you wanted to do. I don't care. I don't care. But you should know, in theory, in terms of analysis, that third one might be a good one in both space and time efficiency-wise. So that's all I care at this point. Converging pointer algorithm is an order n algorithm. Actually, theta n algorithm. The work is proportional to n. Theta n square algorithm work is proportional to the square of n, right? Okay, finally, going to a binary search. Those data cleanup algorithm, we're done. 3 different algorithms. We choose a very simple algorithm, but it can display the time and space efficiency in terms of magnitude of order of magnitude of n. What about binary search? What about in searching algorithm? I mentioned last class briefly. Now we have n square, constant, What's missing? What's coming up? 저번 시간 끝날 잠깐 했잖아. We're missing this part. Log. We're missing this. Binary search. Hopefully doing that. What does binary means? Binary가 뭐야? Binary numbers. 이진수. Okay. What is 이진수? What is a binary number? 01. Okay. What is the number that we use in human beings? Decimal number, right? 0 to 9. So we have a 10 choice. Binary, 0 or 1, 2 choice. 그죠? Log, base of 2 is what? Base 2. Right. We have 2 choice. Binary search. So we're going to use that idea, apply to come up with a better searching algorithm. There. Procedure. 아이고 힘들어. First look name roughly halfway at the point. It's not a sequential search anymore. The name that we try to look, sequential search always n, linear, right? Binary search. I like to find the name somewhere in the middle. If the name equals the name, search is over. If name comes alphabetically before name, blah, blah, blah. And then you're done, you go to the left or right. I explained this already, but let me do it again. 글로 읽으려니까 귀찮죠. It's a bit painful, even though it's a very short sentences. Okay. Let me do this very roughly. Again, list. Give me any name. Just A, B, C, D 하죠. C, D, F, G, H. It says, I'm looking for name. 몰라. Give me anything. C? A? Okay, A 하죠. Which is not in the list. It says, start from roughly halfway in the list. 1, 2, 3, 4, 5, 6. I don't care. It's a 6. Let's take a look at 4. Okay, roughly halfway in the list. G, A, no. But assume this list is alphabetically ordered. C, D, F, G, H, I. 맞지? A, B, C, D. Okay. Then I can decide that G is bigger than A, so it means, and this list, this side have characters only bigger than G, so I don't need to take a look at this side anymore. Half. 0, 1, 0. Okay. So I'm done with the another half. Again, I start somewhere in the middle of this. Okay, let's pick a D. A and D. A smaller than D in terms of sequence in the alphabetical order. So this part, no. Again, 0 and 1. This side only have left with the C. A and C, no. But I don't have any other elements before C. Done. There is no A in the list. So every time I reduce the chance into a half. Half, half. Log. 그치? Log. Algorithm halts, algorithm stops when name is found or not found. So another way of saying it, you narrow the search field. You begin with the 6 elements. Next step, you can just deal with the 3 elements. Next step, log of 3가 뭐야? log 3가 뭐냐? 어? 이걸 외우는 사람 있어? 대단한데? 오씨, 괜히 물어봤다. 아닙니다. 뭐 1점 몇 뭐 어떻게 되겠지, 그지? 그렇지 않겠어? 나 그거를 물어보려고 실제로 대답이 나올 거라는 생각을 못했어요. Anyway, around 1, if I take this 이렇게 하면 모르는구나. 됐다. 됐어. 이거 혹시 안 보여? flow and roof and floor 이런 거 됐어요. 그럼. 쉽게 얘기하면 버리고 반올림하고. 갑자기 한 방 얻어 맞은 것 같아. 로그 3 모르니까 답이 나오길래. Hey, after 3 divide in half, roughly 1. 그죠? Roughly 1. So if I give this list is in this case n is what? 6. If I simply apply log of 또 갑자기 겁난다. I don't know. Maybe 2 point something. 그죠? 2 point something. 뭐 이렇게 되지 않겠어? In this case, I did a 2 comparison. 그죠? I did a 2 comparison. Half. Roughly give me how many comparisons that I did. What I explain here, nice pseudocode ways. Anyway, get values of n, name, and nt. We have seen the data set. Set the value beginning to 1. Set the value of found to no. So probably my loop will be doing this. While I found the elements, while I didn't find the element, I'm going to keep searching. That's why they're going to declare a variable name found to no. If I found my value, the found will be yes. Okay? That's why it says while found is no. Boolean values. Beginning is less than or equal to the end, then do this. 귀찮다. You guys study this and let me know. 또 설명하니까 귀찮다. But it's not so much different from what I explained. They get a number, divide that number into a half, moving around within a smaller list of stuff. But what must be the precondition of all this type of binary search algorithms? What must be the one and only precondition we must meet? 아니야, 그렇지 않아. It doesn't have to be a even numbers. All numbers still okay. It says roughly in the middle. So if number is 7, I can start from 3 or 4. Doesn't really matter. But that's one misconception you can have. 꼭 짝수일 필요 없어요. 거기 그대로 적혀있잖아요. 그래서 roughly in the middle 이렇게 적혀있잖아요. 예를 들어 11이면 그냥 5부터 하든지 6부터 하든지 상관없어요. 어차피 다 한 번씩은 갈 거니까. That's not the condition that I'm looking for. The condition that I'm looking for is your array must be sorted before I can apply the binary search. If this alphabet is not alphabetically ordered, binary search would not work. But here's an idea, not an idea. Here's a problem. What was the sorting algorithm that we take a look at before? And what was the time efficiency of that sorting algorithm? Selection sort. What was the worst case? Was n square, right? So in order to achieve searching algorithm for log n, I might need to do n square algorithm first and then apply this. Then I might be able to have a log n. So there are conditions like this. 이게 바이너리 서치가 내가 원하는 정도의 시간이 나오려면 다 정리가 돼 있는 상태에서만 되겠죠. 정리가 안 돼 있는 상태에서 바이너리 서치하면 어떻게 돼? A 찾으려면 안 되죠? 전혀 못 찾죠? So that's a precondition that we didn't see before in other algorithms. So these algorithms, assuming everything is sorted, given T and N, sorted, A, B, C, D, E, F, G, 1, 2, 3, 4, 5. logarithmics of n base 2, log base 2, n. Number of times a number of n's can be cut into half, not go below 1. Cut into half every single time. As n doubles, log of n increase only by 1. 그죠? That's a property of logarithmics. Log. So log n grows much more slowly than n. How do you show that in the graph that we have looked at before? 분필을 잊어버리지? Again. log of n. log x. Even if n doubles, so it's only increased by 1. If n is really large numbers, eventually this one is much faster. Do you prefer sequential search or binary search? Just according to this graph, I would prefer binary search if you're dealing with the large numbers. So you just make a decision. Worst case and average case comparisons, log n comparisons, worst case, even log n comparisons. Works only on a list that already has been sorted, key part. Do not try binary search on any list. Must be sorted. 아니면 otherwise you're not doing anything. If cut in half, nicely put. I'm looking for name 4. In the list 4 is 1, 2, 3. So I should be going to this side. 아이고 이거는 그려놓은 걸 적으라는 거구나. So 4 in the middle, 2 in the middle. It's okay. You got the idea, right? Every time you make 2 different decisions, the same as this. Okay? 이거 빼버려야 되겠다. 별로 좋은 게 아니네. Obviously, log n growing and goes to that. If it's n squared, 64, 16 times 16. 몰라. It's 32 times 32. It's much bigger. 그죠? You got the idea. Eventually, this. Comparison of n and log of n. 아이고 힘들어. 여기까지 오느라 길었다. We have only looked at very nice algorithms. What about the time complexity of the pattern matching algorithm that we studied? I don't know. Answers right here, but you can just start discuss this in next class, okay? 다음 시간에 마저 다 합시다. Any questions for today? 다시 한번 얘기하지만 컨버징 포인터 셔플 레프트 책에 그대로 나오니까 한 번씩 이렇게 손으로 해봐요. 그럼 뭐 어차피 숙제 하느라 한 번씩 할 테니까. Okay, I'm gonna call out the attendance now. 출석 부릅시다.